All right, today we're going to work through the first problem that students actually encounter in our first and most popular UDEMY course, which is entitled Classical Physics: Journey Through the Laws of the Universe. First, we're going to read through the problem statement, and then I'm going to show you why this is an awesome problem for trying to test students' skills in terms of understanding the language of Lagrangian mechanics, which is calculus of variations. So let's jump right into it. The problem statement is as follows. Suppose that a surface is described by the function z equal to x to the 3/2 as depicted in the figure below, right down here. The question is, what is the shortest path on this surface connecting the 2 points from xyz equal to 0, 0, 0 all the way to xyz equal to 1, 1, 1 on this surface here? So what I have done is I went into my favorite plotting program. I plotted up the three-dimensional surface that we're dealing with, which is z equal to x to the 3/2 right here. It's a nice graphic. And I've also plotted the line that we're trying to find. So we want to find the shortest path that is on this surface. So it has to be on the surface. That's number one. That's the first condition. And number two, the length of that curve on the surface has to be minimized, okay? You hear minimized, that means calculus of variations. So the first thing you need to do is you have to figure out what kind of function, or rather functional, as we've learned, you're going to use for defining the distance between this point to this point for different curves that we're going to try out in the problem. So the first thing I'm going to do is I'm going to show you how we're going to put together that function, okay? So what we're going to do is we're going to take a look at an infinitesimal segment on this curve. So I'm going to take this guy right here. I'm going to blow it up right over here to a big guy right there. And we know that along this curve, an infinitesimal length right there that we're going to call, let's use ds. We know that we could form different segments of this. Now, if we concentrate on the x and the y components of this, we're going to have x, y, and z. What we could say is we're going to have something like this, and then you'd have maybe dx and dy. Okay? And we could find the length of this in the xy plane, the projection of that, by using the Pythagorean theorem, right? So we could technically say that ds is equal to the square root of dx squared plus dy squared. Okay? And that'll give us the distance of this curve projected into the xy plane. But we're really interested in the three-dimensional parameter here, the three-dimensional curve. So what we do know is that if we come over here, we do know that in the x, or rather the zx plane, right, we're going to have another curve. And if this is projected on the x dimension, right, this is going to go like as such. So we could do the same exact thing. And we know that if we take the change in z squared plus ds squared, right, that's going to give us the actual length, because in the xy plane, z is perpendicular to that, right? Right, we can have x, we can have y, and then we can have z here. If we find this guy, ds, so ds is going to be something like this. If we find that projection, this is perpendicular to the z plane. So, right, it's 90 degrees. We can use the Pythagorean theorem again. We get this, and we get the end result. So when we're looking for, we're going to say the actual length around here, we'll call this dl. We can say that dl is nothing more than dz squared plus ds squared, the square root of that. And if we make use of this guy right here and plug that guy in, what we find is that the infinitesimal length along the curve that we're going to use in this problem is defined as follows. So we could plug this guy in, the square of the square root, just gives us the terms inside that square root bracket. And I'm going to put them first. So we get a dx squared plus a dy squared plus dz squared. And that's the actual length that we're going to use. So next, what we need to do is we need to figure out what is going to be the independent variable we want to use, what is going to be the path variable, and how we can manipulate that using calculus of variations to get the end goal that we want, which is minimizing the distance between these 2 points on the surface. So to do that and to progress further, we really need to figure out what variable is going to play which role, which I just described for the path variable and the independent variable, right? What we saw throughout the videos in this course is that, right, we would have a function now. It's going to be a function of, let's say, y sub x prime, and x. We had 2 variables, but here we have 3 variables. So this is why I think this is an awesome problem for testing students' knowledge in terms of their understanding of the language of Lagrangian mechanics, which is calculus of variations, because you have to really understand the underpinnings that are driving this paradigm forward, right? So to solve this dilemma, what I'm going to do is I'm going to make use of a condition we must enforce within the problem, okay? We must assert that the curve is on surface z sub x. Regardless of the curve that minimizes this distance, it must exist on this surface here. In other words, it must be described by this z component here. So in a sense, this is restricting the z values that we have. The z values must conform to this, otherwise we won't exist on the surface. So in order to use that, we can figure out what the path variable is going to be and what our independent variable is going to end up being. And what we're going to do is, we're going to take the derivative of this curve, this z. So we want to take dz dx, and we know that that's an easy derivative, right? That's just 3/2 x to the 1/2. Okay, so we got this guy. And what we see is that if we pull dx out, I'm going to get a nice color here to highlight that. If we get this guy and we pull it out of the square root, right, we're going to get dz dx, we're going to get dy dx, and then we could take this guy, we can plug it into the function L, and that's going to end up giving us 2 variables, right? Because this is a function of x. So that's just going to give us y, it's going to give us x, and we're going to have a dx out here. That's going to allow us to use the nice, beautiful framework that we spent so much time putting together, right? And then we can use our language of calculus of variations and chug forward in the problem, okay? So let's do just that. So we're going to do dl, or rather, I want to use a different color. We want to use our traditional black, or I guess I'll do it over here. So we're going to get dl is equal to, so we're going to pull out the dx squareds, and I'll work through the math for you guys so you don't feel lost. I'm on your team after all. So this becomes dx squared. We pull that out. We get a 1 plus dy over dx, quantity squared. And then we get the dz dx, quantity squared. And then we want to take the square root. So in the long run, we could pull this guy right here, all the way over there. We can plug that guy in there. And when we do that, we end up with dl equal to the square root of 1 plus, now I'm going to substitute for dy dx, y prime sub x, y prime sub x squared. And then when we square this guy, we get 3/2 squared, which is 9/4 times x to the 1/2 squared, that's just x. So down here, what we're going to end up with is 9/4. We get an x. And then we have our dx out right there. So what we have here after we start integrating, or rather, I guess I'll back up a bit. We have the length, the infinitesimal length of the curve, basically right here. And we want to sum up all those lengths to get the entire length along any curve that's going to be connecting these points, right? So whenever you hear that, sum up infinitesimal lengths, that's a trigger for what? Calculus terms. The integral. We want to take the integral. So when we integrate over this guy, if we add up all these DLs, what we get is we're going to get rid of this differential. And, right? The integral of DL is just L, right? So on the right, we have to get the integral. And we're going to go from x1 to x2 because x is our independent variable. And our path variable, which is going to define, we already defined the z term. Now we need to change y along this curve such that we minimize this functional L right here. So y is the path variable. We're going to try a ton of different y's that connect these 2 points. All right, that's the name of the game. So this becomes our functional here. So we have the functional L, which is a function, and I hope my face is not blocking this at all. A function of y, y prime, and x. All right, so this is the framework we're going to use. We have all the framework here. Now all we need to do is what? What's the name of the game? The name of the game is to use the Euler-Lagrange equation to minimize this functional and find the minimum distance between point 1 and point 2 on the surface, which is guaranteed because we made use of this surface equation z sub x. Let's do that now. All right, so we're going to minimize this functional by making use of the Euler-Lagrange equation just as we did throughout our videos, okay? So in our videos, we found that the Euler-Lagrange equation is the following. If the function f conforms to this equation, that guarantees that this curve, which is described by f, is going to minimize the distance between these 2 points. So the question is, if this is the equation we want to use, this is our functional. What is f? So f is going to be the function right here underneath the integral. That's the guy there. And all we need to do really is just plug and chug. We have to take all these derivatives and find what they are in order to make progress. So let's do that right now. So the first one, df dy, where this is f, is obviously going to be 0. Why is that? It's 0 because there's no y present in the function, right? So that's pretty easy. That's sort of like a gimme. So I'm going to write that down. df dy is equal to 0. And the next thing we need to do is figure out what it is for this guy right here, which is a bit more complicated. So we have the partial derivative of f with respect to y prime, the first derivative of y. When we take a look at our function f, it's not as easy as it previously was for this guy, right? Because we have a y prime in here, and right, this guy comes along for the ride. So what we're going to have to do is we're going to have to actually differentiate that guy. So let's do that right now. So df dy prime, what that is equal to. So we have this square root right here. That's going to drop a 1/2 down in the front right here. So we get a 1/2. We get everything that was inside the square root. So that's 1 plus y prime sub x squared plus 9/4x. And then we need to use the good old chain rule. So inside we have y prime, that's squared. So in essence, we just get this 2y prime coming along for the ride. And then we can simplify this to make a nice equation, which is just y prime over, I guess if I back up, I missed something here. So this should actually be a negative 1/2 right there. And that's because this is to the 1/2. We just subtract 1 from the exponent to get that guy right there. So on the bottom, we have this square root term. That's going to be a 1 plus y prime squared plus 9 over 4x. Okay, so we're making progress. We got this guy right here, but we know that we have to take dx. So when we plug all these guys into that, what we're going to find is the following. We find that the derivative with respect to x of this guy right here, which is just y prime over the square root of 1 plus y prime squared plus 9 over 4x. And I'm going to make that look a bit nicer. All of that has to equal 0. So this is our, in essence, sort of equation of motion in a physicsy sense. But this is the guy that we're trying to solve. And as we've seen previously, if you take the first derivative of any kind of function, set it equal to 0, that means that what is inside here, this guy right here, this is equal to a constant we're going to call c. Because if you take the derivative of a constant, that's going to get the end result that you want right there. So using this, we're going to solve our differential equation, and that's going to give us the terms for y that are going to allow us to minimize the distance between points 1 and point 2. Let's do that next. So the first thing we're going to want to do with this guy right here is we're going to want to isolate this y prime. But right now, it's trapped within the square root right down here. So what we want to do, we see we have a y prime squared here. If we square both sides, we can get rid of this radical sign, and then we can move this guy over here and isolate the y prime squared terms that we're interested in, okay? So let's do that right now. So what we end up with when we do that is y prime squared is equal to c squared times 1 plus y prime squared plus 9 over 4x. All right, so we got this guy right down here. I'm going to divide by 1 over c squared and take this guy over to the left. So in essence, what we get is 1 over c squared minus 1, that whole quantity, times y prime squared. And that is just equal to 1 plus 9 over 4x. So the next thing we want to do, which I've shown multiple times in the course and in a lot of videos, is we want to get this guy over here, and then we want to convert it to another constant that simplifies our life and makes it easy. So what we're going to do is we're going to divide this guy. I guess I'll work through it so you guys see exactly what's going on. So we're going to isolate our y prime term. We're going to come over here. We get a 1 over c squared minus 1 times 1 plus 9 over 4x. And next, what we want to do is we want to eliminate the squared term. So all we need to do is we get a y prime equal to the square root of 1 over c squared minus 1. That guy times the square root of 1 plus 9 over 4x. Okay, now what we're going to do, we're going to say this guy, if we have a constant c, we square it, we take 1 over that term, subtract 1, and do 1 over that entire evaluation. Well, what is that? That's just a constant. So we're going to call it a constant d. And then we just get this nice value over here. Y prime is equal to d times the square root of 1 plus 9 over 4x. And life is good. So we have an equation here which looks manageable. We can solve this, right? We don't have to use differential equations. We can just integrate it and get a result. So let's do that right now. All right, so if we move the dx term for the y prime sub x over to the right and integrate, what we're going to get, well, the integral of dy is just y. So we know the function y we're looking for is no different than the integral of d times the square root of 1 plus 9 over 4x dx. All right, so we got an integral we can solve, and you look at this and say, oh, wait a minute, I saw this in Calc 101. What I can do is I can make a nice, beautiful u sub. So we're going to take this guy right here. We're going to say let u equal the term right here, which is just 1 plus 9 over 4x. And when we do that, we need to take the derivative of u so that we can find out what dx is equal to and substitute some information into this integral so we can solve it. So when we take the derivative of that, du dx is equal to 9 over 4. All right. So what we end up with is just, we get 4 over 9. Is that correct? Yes, we get 4 over 9. Du is equal to dx. Okay, so that allows us to take a look at this dx, substitute these parameters in, and then we can proceed with solving this integral to get the function that we're really looking for. So this is equal to, we're going to pop this d term out right there. Okay, we still have the integral. Now we're going to transform this into our u space, which is a function of x. And we just get a 4 over 9 times u to the 1/2. Well, where did that come from? Well, we look at this. That's just the green stuff right in here times the square root of that. And then we get du because we took dx is equal to 4 over 9 du. And now we can solve it. This is an easy integral that we can solve with minimal effort. So what we end up with is we're going to get this d term there. We're going to multiply by 4 over 9 times, well, in order to integrate this, we add 1 to the exponent and then multiply by the inverse in front. So plus 1 to this is like adding 2 over 2, which gives us a 3/2 up at the top. And then we get a 2/3 right there. We get a u to the 3/2. And then what do we have to do? Wait for it. We have to add a constant on, right? Because I didn't define these limits of integration. So we add on a constant, which I'm just going to use an e for. And that's basically the equation we get. So it sort of looks nasty. It sort of looks not as nice. So what I'm going to say is that all these guys, if you take a constant d, multiply by a constant 4 over 9, another constant 2 over 3, what does that get you? That gets you another constant, right? So we're going to simplify our life. We're going to say y sub x is equal to a new constant. We can't use e. I'm going to call it an f. We're going to say, yeah, that's just f times u. Well, u is 1 plus 9 over 4x. And the reason why we're going back to the x domain is because, well, y is a function of x. So u served its purpose to solve this u sub, but we want to get it back so we can actually do something with it. So it's valuable, right? So this is a 3/2 plus e, okay? So that is the nice, important result we get. So we're going to highlight it with our beautiful galaxy ink right here because we're making a dent in the universe. Right there. And next what we need to do is, well, we don't know what this guy is. We also don't know what that guy is. So to actually make this conform, like this is going to span over every kind of solution for these different f and e values. We want it to pertain to this particular curve that goes through point 1 and point 2. So in order to do that, we need to solve these guys using our initial conditions, our boundary conditions, and that's what we're going to do next. So the first boundary condition I would encourage you to use is the easy one. Basically, we take a look at point 1 and we say, well, point 1, we know that y equals 0 and x equals 0. So we can say when x equals 0, y equals 0, plug that in, and we're going to get a very easy result from that. Okay, so what happens is we plug that in, y is equal to 0 is equal to f times 1 plus 0 to the 3/2. That's not going to matter anymore, plus e. And when we get that, we see that 0 is equal to f plus e. And that gives us the following result. We find that f is equal to negative e. All right, so we're going to highlight that in our beautiful galaxy ink. We made another dent in the universe. We're ready to go. All right. All right, so I moved that result up here so we can make use of it in the next equation we consider. And next, what we need to do is we need to take the last remaining bit of information we have, right? So we've used this guy. We used the surface to force the equation we come up with to fall within the surface. We made the curve pass through point 1. The next thing we need to do is ensure that the end result passes through point 2, okay? So that's an important result that allows us to make a dent in the universe. I used our galaxy ink because that's super important. And that tells us that at point 2, x equals 1 and y equals 1. So we can use the boundary condition that y sub 1 is equal to 1. Let's do that right now. So first thing we want to do, we want to plug this guy straight in. F is going to equal to negative e, so we end up with y sub 1, which is equal to 1, is equal to negative e times 1 plus 9 over 4 quantity to the 3/2 plus e. So the next thing I want to do is try and isolate e so we can actually solve for it. And that allows us to solve for e and hence f. Okay, so I made use of this guy right down here. So if we pull out e, we get e times 1 minus the quantity 1 plus 9 over 4 to the 3/2. And that's the result we get. So in order to get e, we're going to have to plop this guy over onto the right, and I'm going to sort of reverse the equations here. So we end up with e being equal to 1 over the quantity 1 minus the quantity 1 plus 9 over 4, but we know that this is just 13 over 4, right? Because 1 is equal to 4 over 4, 4 plus 9 equals 13, that's 13 over 4. So this is going to be 13 over 4. Let's simplify our life here to the 3/2. And that's the result we end up with. So that's what e is going to equal. So we'll highlight that in our galaxy ink. And all we need to do is basically take all this and plug it back into our main equation there. All right, so I brought the results up here. What I'm going to do is I'm going to say we're going to have to bring this guy in there. And this guy has to go whoop, all the way over there, okay? So when we do that, what I'm going to do is this f guy is negative e. It's negative this guy. I'm going to reverse the sign down here. I'm going to take that negative. And what we end up with is the following. Y sub x is equal to... We're going to get the 1 plus 9 over 4x to the 3/2. That is going to be... All this is going to be under 13 over 4 to the 3/2 minus 1. Okay, and the reason why I'm putting this as a common denominator is because f and e have the same guy right here. So f is just negative this. We add that. So e E is going to be this guy, which is the reverse of what I've written down here. So I'm going to put a -1 right in there. And that, ladies and gentlemen, is the final result that we are looking for. So we're really happy. We put that in a box with our Galaxy ink. We made that dent in the universe. So we take this. This is the result we want. And in essence, what we did is we said, okay, we're going to constrain all these different curves to be those which lie on the surface. We're going to employ the Euler-Lagrange equation. And when we do that, that minimizes the distance between here and here for the function L that we derived, which is the length. If the length is minimized and it's going through these points, it has to be this red curve that I have depicted right here. So that's the problem at hand right here for finding the shortest path on a 3D surface. What I'm going to say is that, and what I actually discovered was from some of my students working through this, is that actually there's an alternate way to do this. And this is why I love this problem, because you have to be very cognizant of what variable you select as your independent variable. In this case, we selected X, and your path variable, which was Y in this case. But you can also take the surface equation here, flip this guy by taking everything to the 2/3, and actually substitute in for your X, which would change what you define as your independent variable and your path variable. So if you want more practice with this, with calculus of variations or preparation for Lagrangian mechanics, because this is the language of Lagrangian mechanics, as I've said previously, you can try and solve the same thing by using a different approach. It's possible. My students figured it out, sort of took me by surprise, which is pretty cool. If you actually solve through that, you get the same result. That's going to strengthen your ability to solve these problems and make you more convinced that this is, yes, indeed, the correct result we had here. But if you like that video, make sure you like the video below, subscribe to the channel, hit that notification bell so you can get notified of new videos. And if there's anything you want to actually explore on my YouTube channel, what you can do is you can send me an email at ed@thekaizeneffect.com. I want to figure out what you guys want me to solve for you to make your life easy for free. Absolutely nothing. So send me your problems that you want me to solve. Maybe I'll actually solve that in a video or possibly a live stream. If you want me to do live streams, let me know so we can interact one-on-one. I'll do that completely free. It's up to you. Let me know. I'd be happy to do that. And then I'll see you next time in another video. I hope you enjoyed it. Stay tuned for future content. Thank you.